So I picked these two homework problems because they look a little bit more complicated, and I figured they would give me a good opportunity to explain some things. So I haven't really looked at these too much, just that I decided they'd be good problems, and I wanted to help you with them. So D. Simonton claims that the productivity levels of people in different fields can be described as a function of their career age T with this equation. Okay, and A or B are constants, which depend on the field of work. All right, sounds a little questionable so far. I don't know who this person is. Might want to research them. And career age is approximately 20 years less than the actual age of the individual. So we're kind of rounding, saying people start when they're about 20 years old, their careers, which is very generous, honestly. Many people start later than that, but some people start early. Okay. Wait. Did I interpret that right? You're 45 years old. Your career age will be 25 because you've been doing it for 25 years. If you started at 20 years old. Yeah. Okay. Part A says, based on this model, what age do mathematicians, which have these constants, geologists with those constants, and historians with those constants reach their maximum productivity? So there's a couple ways of doing this. My gut says, let's try to maximize productivity first and then use the constants afterwards. Because if we just maximize it for any A and B, then we can just plug in at the end. So P of T, we want to find a critical point for P of T. Then we need to find when is P prime of T equals 0. Well, what's the derivative of this function up here? We need to use the chain rule. U is going to be this inside, right? U is going to be negative AT. And then like f of u, if you will, is just e to the u. The derivative of this first one should be e to the u times u prime, right? It's f prime times u prime. F prime is e to the u. U prime is just negative a. And similarly for the next one, e to the negative bt times negative b. Same application of the chain rule. Let's simplify this a little bit. This becomes negative a e to the negative at, and now a positive b e to the negative bt. And it's a critical point when p prime of t equals 0. So that's when this is the case. Again, we don't know what a is yet. We could eventually plug it in. But if we can solve before plugging it in, we save ourselves a lot of time. Let's add this guy to both sides to get a e to the negative at equals b e to the negative bt. All right, I'm getting a little nervous. This problem is getting a little tricky. Okay, we want to maximize this productivity. Oh, wait a minute. Yeah, we're basically doing part B at the same time as part 1. All right, it's telling us what the answer is going to be. Telling us what to expect here. So let's keep going. Now we have an exponential equation. We can solve this by taking the natural log of both sides. Natural log of this, natural log of this. I won't be asking a question this messy on a quiz or a test, but it is good practice. And now we use the product rule for natural logs. Remember that the natural log of two things multiplied by each other, which is what we have, two things multiplied by each other, is the natural log of the first one plus the natural log of the second one. We have the natural log of a plus the natural log of e to the negative at equals the natural log of b plus the natural log of e to the negative bt. Looks messy, but we're in a really good spot. Okay? Because What do these two things simplify to? Natural log and exponential functions are inverses. They undo each other. This is the natural log of a plus negative at. This is the natural log of b plus negative bt. We're trying to solve for t. We want t by itself. Natural log of a, natural log of b. We can't compute those yet. Eventually we will, because we know what a and b are going to be. But not yet. Let's get the t's by itself. To do that, let's get the t's on the left-hand side. Let's get the other things over to the right-hand side. Now the left-hand side is a bt minus an at. The right-hand side is the natural log of b minus the natural log of a. We can do two cool things here. Let's remember another property of natural logs. If you divide natural logs, that's the same as subtracting their pieces. Let's go backwards here to combine them. The natural log of b divided by a. On the left-hand side, we want t by itself. Let's factor a t out. What do we get? b minus a. Now we can solve for t by dividing both sides by b minus a. And lo and behold, we get that there's a maximum when t is the natural log of a divided by b all over b minus a. Simonton says, with a little calculus, we can show that p of t maximizes when t is this. This is exactly what we found. The natural log of b over a. Divided by b minus a. All right. We're okay. Whew, I panicked there for a little bit. I did have it right. I just wrote it down wrong after that. Right. This is part B, actually. We actually solved part B right here. Because if we solve part B first, right, if we find this in general, now it becomes much quicker to solve it for A. Right? This is where the maximum is. So now, part A says do it for mathematicians, where A is 3% and B is 5%. And then it says do it again for geologists with 2% and 4%. And it says do it for historians with 2% and 3%. So all we have to do now, we found the maximum for any A and B. So now, just plug it in. And we don't have to do the problem 3 times, essentially. Here's one way you can do this as well if you want to use GeoGebra. You can write natural log of b over a divided by b minus a. And then I think you can just tell it a is 0.03. And you can tell it that b is 0.05. When you do that, you see we get 25. Let's round. We're talking about how old people are, or specifically how many years, their career age. This is going to be about 46 years old, which is really, I think, false for mathematicians, at least. This is a claim about their productivity levels. Oh, I guess it says productivity levels. It doesn't say like ability levels. So maybe they're most productive when they're 46. That's believable. And we can do the same thing with the other ones, right? The geologists, A will be 0.02. and B is going to be 0.04. So that's going to be about 35 years of a career age. That's going to be about 55 years old. Geologists apparently are more productive when they're older. Historians has a B value of 0.03, about 41. Historians are the old people. This is saying this is when their productivities are maximized. This is just I don't know who this person is. This is somebody's claim. Somebody's claim. Take it with a grain of salt. Even the book has a disclaimer. It says this usually can be okay for describing the behavior of groups if it's valid, but don't use this to describe or compare to individuals in a group. Okay? And this whole thing is apparently done in 1988, so who knows? Who knows? Curious about this? Maybe do a little reading about it. Maybe I'll check it out. That's what this guy was saying. Productivity levels, maximizing. Again, probably a little bit more difficult than I would give you, but it is within your abilities. In pre-calculus, we learned these properties of natural logs. In pre-calculus, we learned how to solve logarithmic equations and exponential equations. Okay, so it is something you could be expected to do, but I probably won't ask you to do this on a quiz or an exam. Okay, and if you did it, I would just give you the A and B values, so you wouldn't have to do it for any A and B. Let me know if you have questions or concerns about that. The other homework problem I chose was specifically to give you some practice talking about some of these terms for economics. So the total cost in dollars for Alicia to make Q oven mitts is given by this quadratic Q function. What is the fixed cost? Remember in the last video, I broke up the cost function, right? This is the fixed cost. This is the variable cost. And specifically, this is telling us that each oven mitt will always cost like $1.5 per oven mitt. It's like probably the material cost or maybe some other kind of cost. They're always going to cost at least $1.5 each. And then this is the value that, like, depending on, like, the more she makes, the more the costs are going to go up because maybe we're straining our production capacity. Okay, maybe if we have machinery, then like we have to maybe get more machinery or like run it suboptimally if we're doing too many, or maybe we have to pay for overtime costs for labor, who knows? Okay. But usually there's some kind of penalty to producing too many things. So our fixed cost is just going to be that $64. The marginal cost, well, remember the marginal cost is just the derivative. That's just going to be 1.5 plus 0.02 Q. The average cost, again, we did something very similar earlier. Average cost is just going to be the total cost. All over how many we're producing. And for D, remember we have the shortcut. The total cost, so the average cost is minimized when the marginal cost equals the average cost. Or you could just take the derivative of this and set it equal to 0. Your choice. In the earlier video, I used this method. Let's take the derivative and set it equal to 0, and I'll show you that this also works. The derivative of the average cost function is low d high, the derivative of the top, minus high. Oh, I don't have room for that. Oh, dear, that's the wrong button. This is going to take longer than if I just forgot how to do this. I really didn't want to. Oh. Yeah, you can do something like this. It would have been just faster if I rewrote it. All right, low, d high, minus high, d low, the derivative of the bottom is just 1. Square the bottom and away we go. This is why this shortcut's nice, because this is a lot nicer than this. But here we go. And we want to minimize this, so it'll be minimized at a critical point. Critical point is when the derivative equals 0. Now we need to simplify that numerator. That'll need to still write in red. 1.5q plus 0.02 q squared. Distribute the negative. Denominator still q squared. We solve equations with fractions by multiplying both sides by the least common denominator. When we do that, it cancels on this side and the left-hand side still 0. Let's combine like terms. These cancel out. And then we have plus 0.02 minus 0.01. That gives us 0.01 q squared. And we have a minus 64. Add 64 to both sides and we're almost done. We get q squared is 6400, or q is about 80. Find the quantity that minimizes the average cost. Q equals 80 mits. So say 80 mits. 80 oven mitts. Confirm that the average cost and marginal cost are equal. Oh, okay. So they actually wanted us to do it this way. Well, let's find the marginal cost. Right, for E. The marginal cost, when we're producing 80 mits, well, the marginal cost is 1.5 plus 0.02. Marginal cost is 3.1. Right, marginal cost, $3.10 per oven mitt. The average cost at this production level is 64 plus 1.5, 80 oven mitts, plus 0.01 times 80 oven mitts squared, divided by 80 oven mitts. Average cost is 3.10. So $3.10 per oven mitt. Check. They are indeed equal. So we used calculus to find the minimum average cost with a quotient rule. And we showed you that, yes, I claimed that the minimum average cost will be when marginal cost and average cost are equal. And there you have it. They are indeed equal in this case. Doesn't prove the rule, but it shows that at least the rule holds in this case. Let me know if you have any questions. And there we are. Bye-bye.